All right, welcome. We will talk about convolution. If I manage to close this window. Very good. So convolution, why? It is a useful basic tool. It's not the state of the art for smoothing, but it's an elementary technique that is used as part of more complicated pipelines, like it's an essential part of deep neural networks, which then will give you state of the art in smoothing, can be used for detecting edges, for detecting blobs, or somewhat more complicated shapes, can, generally speaking, be used to extract features. It has really been a workhorse of image analysis ever since images have been processed on computers. Why? Because it's really cheap. Being cheap really mattered in the early days of computer vision. So maybe you need to talk to your parents to ask them, what was the performance of computers at the time. But when you have 8 megabyte, not gigabyte, but if you have 8 megabyte of memory, or if you have 64 kilobyte of memory, to do image processing on it is really, a difficult matter. My predecessor as a professor, that's what he had to deal with, and it's surprising what they accomplished at the time. So it mattered then. It still matters now, as I showed you an example from the previous segment, where we need to process lots of pixels in very little time on relatively modest hardware. And yeah, talking about smartphones. So yes, on the one hand, this budget smartphone has more compute power than a cray supercomputer from the 1970s, which never ceases to amaze me. But on the other hand, it doesn't have a fan, it doesn't have a huge battery, it doesn't have a huge GPU. Yeah? So efficiency still matters. In addition, there's nothing that's better understood than convolution, and we will, especially next time that we meet, talk about how to perfectly characterize convolution filters either in the spatial or in the spectral domain and understand what they're doing. Now today we will talk first about convolution of 1D signals, and then about convolution of 2D signals of images, and generalization to more dimensions is straightforward. Now I've decided to introduce convolution. Maybe it's a small detour, but I've decided to introduce it via non-parametric regression. And I'm showing you here 2 images from this fine textbook called The Elements of Statistical Learning by Hasty, Tibshirani, and Friedman, one of the classics in the field of machine learning. Now, what you see here is the x-axis and the y-axis. And that would be the typical kind of plot that you see for linear regression. We have a measurement, which is on the x-axis, and we have an observation that we want to predict, which is on the y-axis. And well, except that the observations, which are the gray circles here, if you look at them, they will tell you that maybe linear regression is not a good idea. And indeed, these points were generated by randomly from the blue curve that you see. And you see the blue curve is not linear. Linear regression is not a good idea. We need something more flexible. And something more flexible is the so-called Nadaraya-Watson smoothing. And now you've at least learned a fancy word for today. And the result of Nadaraya-Watson smoothing with 2 different kernels is shown here in green. So you see this function which has a little bit, well, it has many, many small steps. And if we use a different kernel, we see this green function. It still doesn't coincide with the blue one because we make this estimate from a finite data sample, but still it's much better. And now, how does it work? I have a mini derivation here. Just to recall, if I want to, so the mean squared estimator is an estimator of location. So if you just say I have a couple of measurements yi, and I want to know what is their center of mass, how do you do that? You minimize over y the sum of the squared deviations of my measurements from y. So how do I do that? I differentiate this objective function with respect to y, giving me the thing written here. And then I say this is the convex optimization problem, and the extremum will be found where this derivative is 0. And here note that I have summation over summation over y of the yi's, and summation over y of this y. So this means in total I have n of these y's, and this is why I have written an n here on the left-hand side in the next line. All right, and then I can solve this and come up with my final estimate, which is just the old center of mass equation that everybody knows. Now, the same thing, but we can say I want to find a weighted center of mass, or my observations do not have the same weight, but observation I has associated with it a weight wi. And then I can do the same kind of calculation, and I end up with this result here. So you see that if the weights are uniform, then if the weights are all 1, then this thing here is n, which is what I had written up here, but they can also be different from 1. Now the next generalization is that I make these weights depend. Now we come to this Nadaraya-Watson setting. The weights depend on distance from a location x. So in other words, I decide that I'm interested in an estimate at location x, and I'm now using a weight function which decays with distance from x. Here I've shown something that looks like a Gaussian, but in reality usually you use weight functions that become strictly 0 beyond some distance. Like this would be a popular weight function, or the so-called Epernechnikov weight function is just a truncated parabola, or another weight function that was shown in the images above is the box weight function, the box kernel. So this would be box. This here would be Epernechnikov or truncated parabola. And this would, for example, be a cubic B-spline. And there are many other weight functions that look almost like the cubic B-spline, do very much the same thing. All right. Now, you see it's the same equation above, except now the weight depends on the distance from the location of interest, which is x. And then my formula looks like this. And you can go over it after lecture if you want to look at this in more time. And finally, now in signal processing and image processing, usually the observations are equidistant, which is this word here. Equidistant means the pixels all have the same distance from each other. Or if I sample a time series, usually the samples are sampled, let's say, 1 per millisecond, so they also have the same distance in time. And then I can write the equation like that. So my estimate at location L is a weighted sum over all observations, weighted with their distance from location L. And this is for normalization. Now, in the example from the textbook, the weight functions were this. On the one hand, here they call it the nearest neighbor kernel, or the box kernel. And on the other hand, the Epernechnikov kernel, the truncated parabola. And so what you see in the image here This is the box kernel, showing the weights relative to this location x0 where I want to make my estimate. And this is the truncated parabola, the Epanechnikov kernel, also centered around my location of interest x0. So these are the weight functions, and then we weight all these observations in the vicinity. So for example, here everything inside this interval gets a weight of 1, and everything outside the interval gets a weight of 0, if we use the box function. And then we end up with these estimates, which from a distance look the same. Yeah? So if I don't zoom in, I have a green line here, which looks broadly like the green line there. But if I do zoom in, again, notice the strong differences. Here I have these tiny steps. Namely, as I move my box, there are observations entering my window and leaving my window. And each time that observation enters or leaves the window, I get a small kink in my estimate. And here I get something much smoother because my kernel decays to 0 slowly. Yeah, so here my kernel has a discontinuity, and there it does not. Discontinuity only in the first derivative. All right, so different filters can produce very different results. And so filter optimization has been a really important topic in computer vision for a long time. All right, now what we have seen, and this is why I talked about this at length, is one example of a discrete convolution. So let's look at this formula again. Ignoring here this normalization, what we have is a summation over I, and then there is L minus I indexing here and a plus I indexing there. And this is the hallmark of convolution. So I can write the formula like this. Same thing, just now I've not written Y and W, but F and G, where let's say F is the filter and G is the one-dimensional signal to be filtered. And this is the definition of convolution. So I can say that F convolved with G at location L is the thing that you see here. And if I had a nice handwriting, the symbol that's used here would look like that. Let me try again. All right, so that's the shorthand for convolution. And actually, if you work with signals of infinite length, or if you use periodic boundary conditions, which is what this PBC here means, periodic boundary conditions, then it turns out that F convolved with G at location L is the very same as G convolved with F at location L. In other words, convolution is commutative. Convolution is also associative. That's a really important result, because it means that, let's say H is my image, G is a filter, F is a filter. Then I can obtain the same result in various ways. I can either first filter my image H with G and then filter the result with F, or I can immediately construct sort of a net kernel, an overall kernel. So I convolve one filter with the other, I obtain a new filter, and then I convolve this new filter with my image. It's a really important equality, which also is very important in practice, because, for example, this may or may not be more efficient than that. And a huge amount of tuning and optimization goes into this, because we're dealing with billions and billions of pixels when we work with video. And then convolution is distributive, so F convolved with G plus H is the same as F convolved with G plus F convolved with H. All right. Now, what type of filters are important? If my filter only has coefficients larger than 0, then usually well, I could construct more bizarre things, but usually these are smoothing filters. And you see two examples here. That would be the boxed kernel, or this would be the Epernechnikov kernel. And I've here drawn a kind of sketch which is typical for signal processing, except my drawing has not been so pretty. So imagine that this is a one-dimensional time series, and then I show the filter coefficients for each, well, lag. And here, for example, I have three coefficients which are 1 in the middle, and the other coefficients are 0. Now, if I want to just shift, this is also a convolution kernel. It's a convolution kernel which is a Dirac delta located at a distance s from the origin, if I want to shift by an amount of s. And of course, I can compute central or non-central finite differences to approximate a differentiation. Now, if I ask you what's the kernel for the second derivative, well, if you know a kernel for a first derivative, then as you know, I can obtain the second derivative by taking two first derivatives. So this is just what I do here. I take a first derivative kernel, convolve it with itself, and I obtain a second derivative filter, which gives me the local curvature. Now, for next week, when we talk about the discrete Fourier transform, this observation is really important, namely that 1D convolution can also be written as matrix multiplication with a matrix that has a special structure, a Toeplitz matrix. Yeah? So, for example, if I want to convolve here my central finite differences filter with coefficients of +1, 0, and -1, if I want to convolve it with this signal, I've just called it here G0 through G5 to be general, then if you compare the equation for convolution, if you compare it with the equation for matrix vector multiplication, so M would be some matrix, V is some vector, then you see that they are basically the same, except that I have some special structure in my matrix, namely Toeplitz structure. So I can rewrite this convolution in this form, and you see that this is a banded matrix with the same element appearing over and over. And if I use periodic boundary conditions, it's important not to forget these things here. And this is typically where mistakes happen if you implement these things by hand, that something's going wrong, in these corner cases, especially in more than one dimension. All right. Do you have questions about 1D convolution? Anyone? Okay, I see nothing. Then let's have a super short break, and then we will go to 2D convolution. Super short, 1 minute enough? I get no contradictions. We will have a super short break of a minute, and then I go on to talk about 2D convolutions, and you please stretch. Thank you. Then we go on with the 2D convolution. So we have now come to images. The formula here is very similar. We have a filter, we have an image, and we multiply the filter coefficients with my image. We sum over the size of the filter, and we do this for all locations which are here called U and V. So this would be the result of F convolved with G at locations U and V. Now, as the hardware has evolved over time, there were times when filters were tiny and times when filters were big. So for example, in the early days, we could only use tiny filters. So 3x3 was all that was possible. Then when it came to deep learning, there was a short period when people proved that big filters work better. And then it took a while until people proved, well, this was all empirical, that actually small filters work better. So it's better to use small filters and more layers. So now we are back at using mostly very small filters and mostly very large images. Now what's special is that in 2D, some filters are separable, meaning my filter at coordinate I and j can be written as an outer product. And I mean this literally. So a 2D filter is, of course, a small matrix. So if I just take a 3x3 filter, to be explicit, I can write this as an outer product between a column vector and a row vector. And this kind of decomposition becomes interesting, in particular, if you work with larger matrices. Yeah, so let's say if this matrix here is 25 by 25, then naively I would need 625 elements for my filter, but here I just need 25 plus 25, which is 50. Yeah, so there's of course a huge savings if your filter does have this kind of low rank structure. And so in practice, this means that if a filter is, and that's the technical term here, if a filter is separable, then I can rewrite my convolution like so. I first convolve all the rows of my image with a 1D filter, and then the result image, I convolve all the columns with the second filter, or vice versa, because we've learned that convolutions commute. Now, sometimes you know that your filter is separable by design. For example, if I happen to use a Gaussian filter, then I know that the Gaussian decomposes into, okay, now I don't know how to draw this. Okay, I'm drawing one Gaussian like this and the other like that. I'm mixing two representations here, so it's not a great picture. So sometimes you know that they are separable by design. Sometimes you have maybe learned a fancy filter, or you've designed a fancy filter and you want to make it separable. And those who have heard about the singular value decomposition, so singular value decomposition, or SVD for short, know that, well, I can find in many cases a low rank representation. So here this was rank 1, but often rank 1 is not enough, but I also don't need full rank, but maybe I get away with the first 5 components or so. And then this can make for huge savings, because in that case, for example, I may need to do 5 convolutions with row and column filters, which may still be much, much cheaper than doing the full 2D convolution with a very large filter, for example. All right. Now, it's good to have implemented convolution yourself once in your life to make sure you understand it. In practice, there are, I think, hundreds, if not thousands, of software engineers in these large companies. Because convolution is such an important elementary operation, there are armies of people working on making this efficient. And so when I here talked about convolving rows or columns, then of course one of the things that really matters is what's the memory layout of your image in the memory. Yeah? So is your image stored row-wise or column-wise? Because if you jump around in your memory access, this is what makes this is what's very, very expensive on modern architectures. So there are many considerations here, and yeah, people have found very, very efficient implementations. I would say, you know, it's impossible to beat any of these specialized implementations by the large companies. Now, no matter whether you work in 1D or in 2D, you have the question of, you know, the corner cases. So on the right is the reference where I took these pretty pictures from. Let's look at this. The blue thing is the image. The red thing here is the filter with its coefficients. And let me just use a different color here. So here you see the filter coefficients. There are 2, 0, 1, 1, 0, 0, 0, 1, 1. Those are not particularly meaningful coefficients. You know, I have no idea what this filter is supposed to do, but it serves the purpose here of showing how this works. So for example, here, if I multiply the filter coefficients with the image content, the image has here been extrapolated with zeros, or this is called zero padding. Then you see I have 2 times 0, which is 0. Here I have 2 times 0, which is 0. 0 times 1 is 0, and 1 times 1 is 1. So summing up all of these things gives me a 1, which is the result that you see here. And similarly, I obtain the result for the other cells. Now, somewhere there is a pretty animation. Let's look at this. So if you implement convolution naively, you know, no SVD decomposition, etc., this is how you operate. You do this pixel by pixel. All right. Now, here, what this image shows you is, here the blue is the input, and in this case, the green is the output, and the desired output here was to be of the same size as the input. And you see that if I now use this gray convolution filter mask, I don't really have enough inputs. So yes, I can extrapolate my image with zeros. So wherever there are these dashed boxes, I would put zeros. But you can see that these zeros, well, they will you know, distort my output. So I will certainly see that in the resulting images. So we have these various choices of what do we want to do in these boxes here. We could put zeros in there, which is called zero padding, or we could mirror the image. So if the image goes from left to right, then I just mirror the image and continue. Or it goes from bottom to top, I mirror the image and continue, which usually gives more meaningful results than zero padding. Or I can use periodic boundary conditions, which is convenient for the discrete Fourier transform, but not very meaningful in images otherwise. And then I can choose what output size I want for my convolution. Just the small part which is not influenced by the extrapolation, that would be valid. Or I want output of the same size, that's what was shown in this picture here. Or maybe I even want to use an even bigger output, which sometimes is necessary. Good. There is also, I'm not going into details here, but I want to mention that there is normalized convolution, which means, for example, for a weight mask that you, in this example here, you would ignore the coefficients out there, and you would recompute the weights for the remaining coefficients so as to only, well, you truncate the filter to the valid part of the input, but you readjust your filter. If you want to know more about this, look it up separately. I don't have time to talk about it now. Good. Then in pictures, I want to show you here from this textbook of Bernd Jähne, who until recently was a professor in computer vision and in environmental physics at Heidelberg University, the effect of various smoothing filters. And now, maybe it's good if you look at these eventually in the OneNote, because this webcam and so on might introduce additional blurring, so you don't quite see what I want to show you here. But what we see is a test pattern, these concentric rings in the top left corner and in the bottom right corner. This is the test pattern. And then you can see the result of applying a large smoothing box filter or a small box filter for smoothing here. And at least on my screen, I see that it strongly smoothes here and there. It's strongly smoothes here and there. But then outside, it does something very funny. So outside, you see it phase inverts. So the test pattern are concentric rings. So this wide ring here, this wide ring in the test pattern, it continues white, but here if you look at the output, it continues as black. So what you see is that the box filter introduces really strange artifacts. And we will understand next time that we meet in terms of the impulse, or in terms of the transfer function in K-space, in Fourier space, of why this is so. So in summary, the box filter is always a bad idea if you want to smooth an image. Instead, you should use a good smoothing filter, such as, here a binomial filter was used, which does not produce these weird artifacts that you've seen for the box filter. And by the way, the best small smoothing filters were developed by Hanno Scharr, who was a physics student and later PhD student at Heidelberg University in the lab of Bernd Jähne, and he's now group leader at Jülich, and he has these filters named after him. Yeah, so Hanno Scharr, the Scharr filters, the best small smoothing filters in terms of rotational invariance. Good. Now, well, we can use bigger smoothing filters. And here, for example, you see these border effects. The image becomes darker on the outside. If you use these derivative filters, then, well, you can highlight horizontal or vertical edges, or you can compute edge strength. This is sometimes used for image sharpening and is also used for all kinds of other applications. Derivative filters are also used to estimate directions, and estimating direction is the same or is equivalent to estimating velocity. Yeah, so also from Bernd Jähne's book here, we see a street view, and a video is, if I have x, y plus time, this gives you a 3D volume. And here, for example, you see cars accelerating over time, and this acceleration you can see as well, different directions in this 3D, or different orientations in this 3D volume, and derivative filters are important for estimating these. Okay, I'm going to skip this and ask if you have any questions right now. Benjamin.
Yeah, just a quick question about the filter or the kernel size, because from my experience, or I work with downsampled images like in a really low dimensionality. And how would we pick them, or how would we choose our kernel or filter size for example, yeah, like full resolution images?
And when you say you work with, what do you mean? Are you using deep networks or are you?
Yeah, exactly, CNNs.
Okay. So I suggest we. So Benjamin, either I will give the. So if we decide to talk about the unit in the lecture, then we will talk precisely about this, about the because the image is then represented at multiple resolutions, high resolutions and small resolutions, and then we can discuss in detail at what's happening in those resolutions. If we decide not to talk about the unit in the lecture, then we will just have a one-to-one conversation about this particular question of yours. Is that okay, Benjamin?
Yeah, okay, thank you.
Anything else? So Yuchen wrote a question in the chat, why there is a 1 and -1 in the corner of the triplets matrix. This is because of the periodic boundary conditions. So usually I say a 1D signal looks like that. When I apply periodic boundary conditions, I say that my signal lives on a ring. Yeah? So for example, let's say there's G0 here, there's G1 there, G2, G3. Okay, I'm making the signal a bit longer now. And now I'm convolving this with a filter. For example, this 1, 0, -1. And so for example, I'm now putting my coefficients here, +1, 0, -1. And excuse me, because I convolve, I have to flip the filter, so it will be -1, 0, +1. And that is exactly the first, so this situation is exactly the first row of this matrix. Now, U10. Okay? Do you want to use your microphone? So what I've shown here was the first row of the matrix. Or if I shift a little bit, let's say I do a minus, different color. I do the -1 here and the 0 there and the +1 there. That would be the second row of the matrix. It would be this row of the matrix. And again, using a different color, the -1, 0, +1, so putting my convolution filter here, would be that row of the, no, sorry, the first one would be that row of the matrix. All right. Good. Man, we are running out of time, but I would still like to show you how to use filters for feature extraction. What do we do? We will move this part to the exercise because it's important for you to know, but I don't want to go completely over time. I will tell you about this next Tuesday at 3:15 to avoid running over time. For today, thank you very much. And instead of knocking on the table, if you like, you can give me a clap. And I will say thank you for good questions. And 2 weeks from now, we will see that we will try that with camera and see if you're comfortable with that, and that would make maybe for a livelier experience. Okay. Thank you very much. See you then. Bye bye. Stay safe.